specializing in artificial intelligence and machine learning. In this session, I'll take you through the basics of machine learning, starting from what is machine learning, through to the types of machine learning, what is deep learning, and an overview of the machine learning pipeline. We'll begin by taking a look at how machine learning can be used to address common situations more effectively than traditional programming approaches. Let's take a common use case, product recommendations on a shopping site. Let's say you've been tasked with creating the back-end application that will provide product recommendations to customers based on their past purchases. Classical programming is traditionally how these needs were handled in the past. Programmers would set up rules that said, if this customer purchased product X in the past, show them product Y, because there was some established relationship between those two products. While this occasionally prompts customers to make that second purchase, it required programmers to explicitly define and set these rules. They couldn't take very much additional context about the customer or the products into account. In addition, customers are unique, and just because one customer was interested in products X and Y, that doesn't mean most or even many customers will be interested in both products as well. Finally, even if you were to spend the time developing more complex prediction rules, whenever a recommendation needed to be made, the application would have to run through all the appropriate rules all over again. As more rules are added, the process takes longer to return a result, meaning customers are waiting for those recommendations to load and likely getting frustrated and moving on to another page. Machine learning, in contrast, would let us use a variety of data collected in the past to automatically derive the patterns hidden in that data. The patterns are then used to create the model, which is applied to new data to provide a more well-informed and adaptive prediction. In this example, we'd be able to use the customer's purchase history in combination with data of customers and sales site-wide. We can use machine learning to identify the patterns between past customers and sales, then apply those patterns to new customers in order to provide better recommendations to them. So you might be wondering, what is a model exactly? A model in machine learning is the trained algorithm you use to identify patterns in your data. The key there is that it's trained through the machine learning process. It isn't created manually by programmers setting up rules like in classical programming. Let's look at a very simple example algorithm. Now, this algorithm has been simplified from what you might use in a real environment, but it shows the two key components of a machine learning algorithm: features and weights. Now, don't be too scared because there's a bit of maths here. It's actually quite simple, and we're going to step through it together. Features are the parts of your data sets that are identified as important in determining accurate outcomes. For example, with our product recommendation algorithm, the first feature might be whether or not the item is a hat. These features have to be expressed mathematically, so in this case, our model will convert a yes into a 1 and a no to a 0. But the key to machine learning is the idea of context. That's where weights come in. Weights represent how important an associated feature is to determining the accuracy of the outcome. So a feature that has a higher likelihood of contributing towards making an accurate prediction has a higher weight, and vice versa. In this case, our model has been trained and has determined that because this customer has purchased 8 hats in the past, that translates to a weight of 0.8. Now, it's important to note, once again, that this is a very simplified version of what really goes on. As this session continues, your understanding of weights and features will grow in depth. But for now, this is the most critical part of understanding how weights and features work in an algorithm. Let's look at the next set. This second feature has to do with whether or not a product is from a particular brand. The product is from that brand, so that converts again into a 1. The second weight says that since 2 out of the 8 items this person bought in the past were from that brand, that results in, you guessed it, a weight of 0.25. If this was a very simple model, this is what you'd end up with. Now let's say the standard for whether or not to recommend is if the final result is greater than 1. The model performs this calculation and finds the final value to be 1.05. Therefore, this product is an acceptable recommendation. So if we're not using a traditional programming approach, you might be wondering, well, what types and kinds of algorithms are actually used for machine learning? Before we look at the kinds of algorithms, let's take a step back and look at the different types of machine learning. There's supervised learning, where a model uses known inputs and outputs to generalize future outputs. There's unsupervised learning, where the model doesn't know inputs or outputs, so it finds patterns in the data without help. And there's reinforcement learning, where the model interacts with its environment and learns to take actions that will maximize rewards. And then there's deep learning, which is a subset of machine learning. These algorithms learn by using artificial neural networks. Now that's not listed here, but we'll talk a bit about deep learning a little bit later. It's important to know the types of machine learning because the type will guide you towards selecting an algorithm or algorithms that make sense for solving your business problem. First, let's talk about supervised machine learning. Supervised learning is a popular type of machine learning because it's widely applicable. It's called supervised learning because there needs to be a supervisor, a teacher who can guide the algorithm to learn. A supervised algorithm learns by being provided with example data, with a description of each piece of data. Now that's known as a label. In this example, we have some pictures and they are labeled as cars. The model is trained on this labeled data so that it can accurately identify whether a new picture it hasn't seen before is a car or not. Within supervised learning, there are different types of problems which can be addressed. These can be broadly categorized into 2 categories: classification and regression. Within classification problems, there are actually 2 types. The first are binary classification problems. Think back to the example provided before about identifying fraudulent transactions. The target variable in this example is limited to 2 options: fraudulent or not fraudulent. This is an example of a binary classification problem. You are classifying an observation into one of 2 categories. There are also multi-class classification problems. These problems classify an observation into one of 3 or more categories. Pretend you have a machine learning model that predicts why a customer is calling your store so that you can reduce the number of transfers needed before getting the customer to the right customer support department. The different customer support departments in this case represent the variety of potential target variables, which, needless to say, could be many different departments, far greater than just 2. Finally, there are regression problems. In a regression problem, you're no longer mapping an input to a defined number of categories, but instead to a continuous numerical value, in other words, a number. One example of a regression problem is predicting the price of a company's stock. On this slide, a regression-based algorithm is predicting that tomorrow the stock price for a company will go up from $113 per share to $127 per share. So that's supervised learning. Now let's talk about unsupervised machine learning. Sometimes all we've got is the data without any description of what each piece of data is. In unsupervised learning, labels are not provided for the data like they are with supervised learning. In this case, we obviously can't predict labels for unseen data, as the training data doesn't even have labels, so the algorithm has no idea what the data is. However, the unsupervised algorithm can identify patterns in the data. A common subcategory of unsupervised learning is called clustering. This groups data into different clusters based upon similar features in order to better understand the attributes of a specific cluster. For example, by analysing corporate customer purchasing habits, unsupervised algorithms are capable of identifying groups of corporate customers as originating from small or large companies. It may be sufficient for smaller companies to purchase basic cloud hosting resources, while larger companies may be more likely to purchase entire cloud solutions, including advanced security, dedicated private connections, virtual private clouds, and more. Clustering in this situation might help you realize that you need to come up with a different marketing strategy for different sized companies. The advantage of unsupervised algorithms is they enable you to see patterns in the data you are otherwise unaware of, like the existence of two major customer types. Another use case for unsupervised learning is anomaly detection, such as this speed camera example. This model is designed to detect potential hardware failures of speed cameras by looking for anomalies in the data. In a classical programming solution, every data point outside of a clearly defined boundary would have to be evaluated as a potential failure. But with unsupervised learning, models can identify what are simple outliers, such as people driving at very high speeds at random points during the day, and what is more likely to be a result of hardware failure, a high volume of extremely high speeds recorded over a span of time. So that's unsupervised learning. Let's now talk about reinforcement learning. Take the example of AWS Deep Racer, as shown on the slide. In the AWS Deep Racer simulator, the agent is the virtual car, the environment is a virtual racetrack, the actions are throttle and steering inputs to the car, and the goal is completing the racetrack as quickly as possible without deviating from the track. The car needs to learn the desired driving behaviour to reach our goal of completing the track. To learn this, we'll use rewards to incentivise our model to learn the desired driving behaviour. In reinforcement learning, the thing driving the learning is called the agent. In this case, it's the Deep Racer car. The environment is the place where the agent learns, which in this example would be the racetrack. The agent has a goal within the environment. In the case of Deep Racer, it's completing a lap around the track as fast as possible, but without going off the track. When the agent performs something in the environment, such as steering, accelerating, and braking, it's called an action. Actions which get the agent closer to achieving its ultimate goal, in this case completing a lap quickly, result in a positive reward being issued. In other words, good decisions are rewarded. Conversely, poor actions are not rewarded, or they're issued a penalty. Over time, the agent learns that to maximize rewards, it needs to perform actions which gets it closer to its goal. Now that we've talked about the three categories of machine learning, let's talk a little bit about deep learning. Deep learning is a subset of machine learning. These algorithms learn using artificial neural networks. Let's dig into that a little. Deep learning represents a huge leap forward in the capabilities for artificial intelligence and machine learning. While the theory for deep learning goes back decades, the hardware required to run deep learning problems wasn't generally accessible until very recently. But now that it's available, we're able to use deep learning to address problems more complex than we could before. To demonstrate the leaps between these three categories, we can use the classic example of machines that can play chess. With classic artificial intelligence, the machines couldn't learn anything that wasn't directly given to them in code. So a machine could play chess based on rules that were provided, but any improvements to its strategy would have to come from a programmer explicitly calling them out and programming them in. With machine learning, as we've learned in this session, chess-playing machines can learn and improve their chess skills by doing things like analysing past chess games that were played by humans. They could be provided